Hello everyone, this is Professor Ng Chi Kun from UNIMAS. In this video, I'm going to show you a lecture on two-way spanning solid slabs, or in short, we call it two-way slabs. So first, we look at the slab action, analysis and design. When floor slabs are supported on four sides, two-way spanning action occurs as shown in figure 5.3a as in this figure here. So in this figure, we see that the loads are transferred in two directions. So in this case, the loads are transferred in two ways like this, where this is 45 degree. So these loads will be transferred in this direction. This load will be transferred in this direction. This trapezoidal load will be transferred in this direction, and this triangular load will be transferred in these directions to the respective supporting beams. In a square slab, the action is equal in each direction. In long, narrow slabs where the length is greater than twice the breadth, the action is effectively one way, as shown in this figure here, in which we have looked at the design in the previous lecture, where the load is only transferred in one way direction, this way. So in this case, we design a slab where the slab dimension is 1 meter, okay, and then the span is in this direction, where this beam and this beam is carrying the slab. Okay, so this beam and this beam are not carrying the loads of the slab in a one-way slab. Slabs may be classified according to the edge conditions. They can be defined as follows. First, simply supported one-panel slabs where the corners can lift away from the supports. A one-panel slab held down on four sides by integral edge beams. The stiffness of the edge beam affects the slab design. So in this case, we call it a restrained slab, okay, in which we will look at the design later. Slabs with all edges continuous over supports, and then the fourth type is a slab with one, two or three edges continuous over supports, and the discontinuous edges may be simply supported or held down by integral edge beams. First, we look at simply supported slabs. The design of simply supported slabs that do not have adequate provision either to resist torsion at the corners or to prevent the corners from lifting may be made in accordance with BS 110 Part 1, 1997, Clause 3.5.3.3. This clause gives the following equations for the maximum moments: MSX for the LX direction and MSY for the LY direction at midspan on strips of unit width for spans LX and LY respectively. So MSX is the moment in the LX direction. So in this case, we have alpha SX times the ultimate design load times LX square. And then MSY in the LY direction is alpha SY times the ultimate design load times LX square. So in these equations here, LX is the shorter span, and then LY is the longer span. And then N is the total ultimate load per unit area, which is the ultimate design load, which is 1.35 GK plus 1.5 QK. And then alpha SX and alpha SY are the moment coefficients from table 3.13 of BS 110 Part 1, 1997. The concrete strips and locations of the maximum moments are shown in figure 5.4a as in this figure here. So in this case, we have 1 meter strip in the LX direction where the span is LX, and then we have 1 meter strip in the LY direction where the span length is LY. So for LY we have MSY, and then for LX we have MSX, and then each of the strip is taken as 1 meter width as what we have used in the one-way slab design. And then at the supports here, we assume that the support and the slab is not connected integrally. Okay, so there is no integral action in between the beam and the slab. So in this case, the slab is free to rotate when action is on the slab. Okay, so meaning that we have a true zero moment at the support there. Some values of the coefficients from BS810 Part 1 1997 table 3.13 are given here. So in the design guidebook you can refer to table 3.13 from BS810 Part 1 1997. So here it gives alpha SX value for different Ly over Lx values, and also alpha Sy value for Ly over Lx of different ratio. So from BS810 Part 1 1987 table 3.13 just now, if Ly over x is equals to 1, then we get alpha Sx equals to 0.062 and alpha Sy equals to 0.062. And if Ly over Lx is equals to 1.5, then alpha Sx is equals to 0.104 and alpha Sy is equals to 0.046. When Ly over Lx increases, the shorter span takes an increasing share of the load. So if we have a slab like this as compared to a slab like this, the shorter span will take more loads in this case, where this is the span in the shorter span direction, Lx. So you see that more load is transferred in the shorter span direction as compared to a slab like this. Okay, so this one has more load as compared to this. And then as for shear on this supporting beam here, okay, we take 1 meter strip of the slab here, and then this total load within this area here of a 1 meter strip is the shear transferred to this supporting beam here, okay, per meter length. Okay, so for the shear here, then you take this strip of loading and calculate what is the total load within this area. Okay, same as for the shorter span, the beam supporting the shorter span of the slab will carry a shear force of equal to the total force on this 1 meter strip times Lx over 2. That will be the shear force transferred to this beam per meter width. Same as for this side of the beam. So the shear force will be this area of loading transferred to this beam here as the shear on this supporting beam. The tension reinforcement can be designed using section 6.1 of Eurocode 2, same as for beam design, okay, and also the same as for the one-way spanning slab. The simplified rules for curtailment given in figure 5.1 apply. The generally assumed load distribution to the beams and the loads causing shear on strips 1 meter wide are shown in figure 5.4c as I have explained just now. So the shear forces in both strips have the same value. So if you notice that the shear of this area load transferred to this beam is the same as the shear transferred to this beam, which is equals to the load applied on this shaded area. Okay, so these two areas are the same. Okay, so the shear resistance is checked using section 6.2.2 of Eurocode 2, similar to one-way spanning slab. The deflection of solid slabs is discussed in section 7.4 of Eurocode 2, where it is stated that in normal cases it is sufficient to check the span to depth ratio of the unit strip spanning in the shorter direction, because the shorter direction is carrying more load as compared to the longer span direction. The amount of steel in the direction of the shorter span is used in the calculation. Crack control is dealt with in section 7.3.3 and 9.3.1 of Eurocode 2. Now let us look at restrained solid slabs. So first we look at the design and arrangement of reinforcement. The design method for restrained slabs is given in BS 110 Part 1, 1997, Clause 3.5.3.5. In these slabs, the corners are prevented from lifting and provision is made for torsion. The maximum moments at midspan on strips of unit width for spans LX and LY are given by, so MSX, which is the maximum moment in the shorter span direction, is beta SX times NLX square, and MSY is given by beta SY times N LX square. So N is the ultimate design load per unit area, and then LX is the shorter span dimension. And beta SX and beta SY are the moment coefficients from table 3.14 given in BS 110 Part 1, 1997. The clause states that these equations may be used for continuous slabs when the following provisions are satisfied. The characteristic dead and imposed loads are approximately the same on adjacent panels as on the panel being considered. Second, the spans of adjacent panels in the direction perpendicular to the line of the common support is approximately the same as that of the panel considered in that direction. The moment coefficients beta Sx and beta Sy in the equations above are given in BS 110 Part 1, 1997, Table 3.14, as I mentioned just now. Equations are also given for deriving the coefficients. 9 slab support arrangements are covered, so the first 4 of which are shown in figure 5.5a. The locations of the moments calculated and values of some coefficients from the table are shown in figure 5.5b. So first let us look at how do we determine the support conditions. So in case 1 here, okay, it's continuous over all 4 sides. Okay, so it is classified as an interior panels where all 4 sides of the supports are continuous. So this is case 1 in our slab design. And then for case 2 here, we have continuous edges at these 3 sides here, and this side is discontinuous. So in this case, we have one short edge, this continuous. So this is case number 2 in our slab there with one short edge discontinuous. Okay, so this is case 2 in our slab layout just now. And then for case 3 here, we have continuous edges on all these 3 sides, and then this side is discontinuous. So this is considered as one long edge discontinuous. So we have one long edge discontinuous here, which is case number 3 in the slab layout. And then all these values are the beta Sx, and then this value on this row here are the beta Sy values. Okay, so there is only one beta Sy value for each of the support conditions, because all these beta Sy values are irrespective of Ly over Lx ratio, where the beta Sx values are dependent of the Ly over Lx ratio. And then for case 4 here, we have continuous edges here, and discontinuous edges here and here. So in this case, we have two adjacent edges discontinuous. So two adjacent edges discontinuous is given by this row here. So we have this as case 4 in our slab layout. So the other 5 support conditions are two short edges discontinuous, two long edges discontinuous, three edges discontinuous with one long edge continuous, three edges discontinuous with only one short edge continuous, and then we have the final support condition is four edges discontinuous. So for example, we look at the case number 4 design here. So we have Lx in this direction and Ly in that direction. Okay, so in this case, how do we determine the bending moments? Okay, so we use the beta Sx and beta Sy value from table 3.14 of BS at 110 part 1 1997. The first example here is Ly over x equals to 1, so meaning that this panel is a square panel. Okay, so this is for Ly over Lx equals to 1, and then we have two adjacent edges discontinuous. Okay, so for the short span moments we have two. So one moment is moment number 2. Okay, and also we have moment number 1 at the continuous edge. So at this position here we have positive moment and we have negative moment across the support. And then the moment here we assume that is 0, although there is integral action in between the supporting beam and the slab. So we will cater for that later on in the design consideration. But first we assume that is 0 moment at the discontinuous edge. So by referring to table 3.14, so for square panel we look at this column here where Ly over Lx is equals to 1. Okay, and then we have these two adjacent edges discontinuous. So we look at this row here. Okay, so for MSX we use beta Sx. So beta Sx for Ly over x equals to 1 is 0.047 for the negative moment at continuous edge. Okay, so meaning that for position 1, beta Sx is 0.047. And then for position number 2, we have positive moment at midspan. So the beta Sx value is 0.036. So the positive moment at location 2 near the midspan of Lx is 0.036. So we have negative 0.047 because it's a negative moment here, and we have position 2 with 0.036 for the positive moment there. Next, we look at the moment for the long span. So long span is Ly. So Ly is in this direction. So moment at location 2 is the midspan moment for Ly direction, and the moment at location 3 is the support or negative moment for the long span Ly. Okay, so from table 3.14, for beta Sy, we look at this column here. So for negative moment at continuous edge is 0.045, and then for positive moment at midspan we have 0.034. So at location 3 here we have negative 0.045. We put in a negative there to indicate that it's a negative moment at the supporting beam. And we have positive bending moment over here at location number 2, which is near the midspan for the Ly direction with beta Sy equals to 0.034. Okay, so in a square slab, by right, that this 0.047 should be equals to the coefficient, which is 0.045, but this is just decimal errors in determining the moment coefficients. Okay, same as for this 0.036, supposed to be the same as this 0.034 also. Okay, so for a square slab, the coefficients should be similar for the midspan and should be similar for the support as well. Okay, but they are just due to decimal errors. And then if we have a rectangular slabs like this with supports over here and supports over here that are continuous, and this continuous over there. Okay, so in this case Ly over Lx is equals to 1.5. Okay, so for the short span direction, the moment for location 2 and the moment for location 1 will be determined from table 3.14 using Ly over Lx equals to 1.5. So now we look at this column here, 1.5, and then negative moment at the continuous edge, the beta Sx coefficient is 0.078, and then positive moment at the midspan is 0.059. So for this one we put a negative sign because it's a negative moment. Okay, and then for beta Sy value we look at this column here. So beta Sy value is the same regardless of Ly over Lx ratio. So it's still 0.045 and 0.034. So in this case, we put the negative sign for 0.045 to indicate that it's a negative moment. So therefore, for the short span, we have negative 0.045 0.078 at location 1 here, and we have 0.059 for location 2 here for the positive bending moment near the midspan of LX direction. And then for the long span direction, we have moment at location 2 and moment at location 3. So at location 3 we have beta sy equals to 0.045 but it's negative. And then at location 2 we have 0.034, which is a positive bending moment at location 2. So if you have adjacent panels with markedly different support moments, okay, so for example you have slab layout like this, okay, so you determine the moment from this panel here for the support moment here, okay, it may be different from the moment that you determine from this slab here where you determine the support moments as well. So at this support there is one moment, one negative moment from this slab here, and then another negative moment from this slab here. So these two values may be different, okay? So the moment coefficients in table 3.14 of BS-A10 part 1 1997 apply to slabs with similar spans and loads giving similar support moments. So if the support moments for adjacent panels differ significantly, the adjustment procedure set out in clause BS-810 part 1 1997 of the code must be used. So this case is not discussed further in this lecture. Okay, so we assume that both sides are having similar spans. And then for shear force and actions on supporting beams. So shear force coefficients beta Vx and beta Vy for various support cases for continuous slabs are given in table 3.15 of PS 10 part 1 1997. The shear force on slabs per unit width or the design loads on supporting beams per unit length, uniformly distributed load, are given by Vsx is equals to beta Vx times the ultimate design load N per unit area multiplied by Lx, which is the shorter dimension of the slab. And then Vsy is equals to beta Vy times N times Lx. Some coefficients for a slab with two adjacent edges discontinuous are shown in figure 5.6a, and also the load distribution on a beam supporting a two-way slab is shown in figure 5.6b. So for an example, now we want to look at the shear force at location 1, 2, 3 and 4 in this figure here. So first of all, we look at a square slab. Okay, so we look at all the shear forces at these four supports. So this is 1, 2, 3 and 4, and this is for Ly over Lx equals to 1. So now we look at two adjacent edges discontinuous. So meaning that we look at this row here, and Ly over Lx is equals to 1. Okay, so at the continuous edge we have 0.4 in the Lx direction, and at the discontinuous edge we have 0.26, okay, in the Lx direction, and then in the Ly direction we have also 0.4 for the continuous edge and 0.26 for the discontinuous edge. So meaning that at location number 1, which is for the short span direction at the continuous edge here, so it is 0.4, okay, and then at location number 2, which is the Lx direction, or the beta Vx is 0.26. 0.26 over here. And then for the long span direction Ly, okay, we have continuous edge at location 3 and discontinuous edge at location 4. So we have the discontinuous edge of location 4 of 0.26 at location 4, and at the continuous edge 3 here we have 0.4 for the beta Vy value. If we have a rectangular slab like this with continuous edge here and continuous edge here, and this continuous edge here and this continuous edge here, so now we look at the shear at each of these location. Okay, so this is the Lx direction, which is for 1 and 2, and then we have the Ly direction, which is for location 3 and 4. And in this case, if we have Ly over Lx equals to 1.5, we look at this column here. Okay, so we have continuous edge for the short span direction is 0.54 for the beta Vx value, and for the discontinuous edge, the beta Vx value is 0.35. And then for beta Vy value, which is for the long span direction, okay, we have 0.4 for the continuous edge and 0.26 for the discontinuous edge. So for the short span direction at the continuous edge, we have 0.54 for location 1, and then for the short span direction at location 2 is the discontinuous edge, so we have 0.35. And then for the long span direction, location 3 is the continuous edge of 0.4 for the beta Vy values, and then for location number 4, the discontinuous edge, the beta Vy value is 0.26, as we have determined from table 3.15 of BS 10 part 1 1997. And this figure here shows the arrangement of load on the slab. So we assume that the slab load is a uniformly distributed load for determining the shear forces at the supporting beams. For deflection, the deflection of solid slabs is discussed in section 7.4 of Eurocode 2, where it is stated that in normal cases it is sufficient to check the span to effective depth ratio of the unit strip spanning in the shorter direction. The amount of steel in the direction of the shorter span is used in the calculation. For cracking, so crack control is dealt with in sections 7.3.3 and 9.3.1 of Eurocode 2. That's all for the lecture in this video. Thank you very much for listening.